talk about some other ways that we can work with the ideal gas law. And a problem that you just worked, in order to get N for PV equals nRT, I gave you grams. And so you had to say, 7.24 grams of ammonia, and then you had to convert using molar mass, so 17.04 grams in 1 mole of ammonia. Find your moles, then plug it into PV equals nRT. Well, if we say that N is the number of moles, what I did is I took the mass, little m, and divided it by the molar mass. Don't know what that was? All right. So that's really what I did, wasn't it? I took the 7.24 and divided it by the molar mass. So what we can do is we can take this in and plug it in here, and we get PV equals little m RT over big M. Now, and that makes it a one-step process. You could still do it the way that you did here in the bell ringer, where you converted to moles and then plugged it into PV equals nRT. Where this version of the formula comes in handy is when we use it to solve for molar mass. It just makes it a whole lot less complicated. And a lot of times we do use PV equals nRT to figure out the identity of a gas, and we can do that with molar mass. Now, if I take this version that we're looking at right here and solve for pressure, so I'm going to divide both sides by V, I get something else here. Mass divided by volume, what is that? Density. All right, so it's pressure equals D, which is density, RT, over molar mass. You can use this version if you're given the density. That'll take care of that, which you can also use for identification purposes. And that also will help out a whole lot. I call this one pressure equals dirt over massive mole. Molar mass helps out. All right. Then again, those are just some other ways. The only one that's given to you for the test is PV equals nRT. All right. Oh, there we go. All right, volume-mass relationship of gases. We're going to introduce a sort of new conversion factor. It's one you already know, just with a little twist to it. So measuring, comparing volumes of gases. Gay-Lussac's law of combining volumes of gases. We know that if we have a balanced equation, it tells us a little bit about the relative amounts of each of the substances in there. We know that from the mole ratio. We can go from 2 moles of hydrogen, it's going to combine with 1 mole of oxygen to form 2 moles of water. We can also make that into molecules. 2 molecules of hydrogen are going to react with 1 molecule of oxygen to form 2 molecules of water vapor. Same thing we can do with volume. So as long as they are all gases and we're not changing any conditions, 2 liters of hydrogen gas combining with 1 liter of oxygen gas is going to give me 2 liters of water vapor. So that is your volume ratio. We use it just like mole ratio. The numbers are coming from the exact same place. The 2 for 2 liters of hydrogen comes from the 2 in the balanced equation in front of H2. There are quite a few conditions on when you can use volume ratio, and we'll talk about those here in just a minute. All right. Avogadro not only had a number, he also had a law, and actually that's how he came up with his number. Most of our early scientists were dealing with gases, and so he was dealing with gases and found equal volumes of gas at the same temperature and pressure contain equal number of molecules, and that led him on his way to his Avogadro's number. All right, molar volume of a gas. Remember, when we see molar in front of something, it means per mole. So we're talking about the volume of a gas per mole that we have. Now, we can figure this out if we're looking at standard pressure, I believe. All right, yeah, standard molar volume of a gas. Standard means it is under standard conditions. What are our standard conditions of pressure and temperature? and temperature is 0 degrees C, but of course in any gas law it has to be in Kelvin, 273 Kelvin. So if we're dealing with just 1 mole of a substance, we can figure out that volume. You can use PV equals nRT. We'll just solve for V. So that's nRT over pressure. And then if we plug these numbers in, 1 mole times 0.0821 liter atmosphere mole K times my temperature, 273 Kelvin, over my standard pressure, which is 1 atmosphere, you're always going to get the exact same answer. What is that when you calculate? Atmospheres cancel. Calculate? 22.4 every single time. All right, now since we use standard conditions a whole lot, that's why we call them standard, we've actually made a little shortcut. And this you will have access to on the green sheets or the reference tables. 22.4 liters per mole for any gas at STP. It is at standard temperature and pressure. Since we can use this, and it is a shortcut for using the ideal gas law, we will use it because you guys are into shortcuts. Our new strategy is going to be, when we see STP, we write down 22.4 liters per mole. Because if it says STP, we can use that conversion factor. It doesn't mean we necessarily will, it means that we can. All right, so let's see this in action. I've got this next problem here. You need 0.058 moles of NO for an experiment. What volume of NO gas would you need at STP? Oh, I see STP, so what are we going to write down? 22.4 liters per mole. Oh, all right, so we start here, 0.0580 moles of NO. And now I want to go to volume. If only there was a conversion factor I could use to go from moles to liters. If only. Yes, the 22.4 liters per mole. Mole is here, mole has to go here, and in 1 mole there are 22.4 liters. Successfully converted. All right, how many sig figs do I need? 3. Remember that leading zeros are not significant, but trailing zeros are in numbers with a decimal. We need 3 sig figs, so I got 1.30 liters of NO. Everybody okay with that? All right, so we're going to talk about stoichiometry of gases. Here we're going to hit again volume ratio. I already told you we get it from the balanced equation. Always make sure your equations are balanced. Don't try and ever do any stoichiometry problem with an unbalanced equation. Volume ratio, it has certain criteria that it has to fall under in order to be able to use it. You can't use it all the time like you can mole ratio. Volume ratio can only be used to convert between gases under the same conditions. So they have to be gases, and there can be no mention of pressure or temperature changing at all. Either they will say that they don't change, or they make absolutely no mention of it changing whatsoever. I have seen this type of problem on, well, you're going to see it on your homework, you're also going to see it on your test, and I have seen it on that final exam, or at least the release copies. I have students, it's super easy, but if you don't know to use volume ratio, it makes you really, really confused. All right, the types of problems always look the same. This was one here. You're going to have a balanced equation, because you're going to have to move from one thing to another, and they give you one number. That's it. one number, it's a volume, and they're asking you about the volume of something else. And you have a balanced equation. That means volume ratio. All right, let's look at this one. So I have 708 liters of NO2. And they want to know what volume of NO. All right, so we check to see if we can use volume ratio. Are they both gases? Yes. And are the conditions the same? Yes. In this one, they actually tell us that they are the same, but if they make no mention of it changing, you have to assume that they are the same. So we start with 708 liters of NO2. And because we have determined we can use volume ratio, that's what we're going to do. Liters of NO2 are on top, so liters of NO2 have to go on the bottom to liters of where the question mark is, NO. And then you fill it in with the coefficients. The coefficient for NO2 from our balanced equation is 3, and the coefficient for NO is an understood 1. Liters of NO2 cancel out, and we're done with this problem. Let me sig figs. 3. And so I get 236 liters of NO. Okay, like I said, volume ratio, very, very easy to actually perform. That was a simple problem, but I have students who get confused and don't know they can use mole ratio, and they do stoichiometry kind of around the world, and they never really feel very good about it, so they just kind of keep going, and they get it wrong. All right, but volume ratio, they have to have gases and same conditions. All right. Now we're going to get into volume mass and mass volume calculations. We are going to have to use some stoichiometry here, and we may have to use the ideal gas law. Whoops. Let's try that again. The first type of problem is a problem that is at STP. So two types of problems, one at STP, one not at STP. All right, so this first one, I actually balanced this equation for you. Of course, you would want to balance an equation. This one's a little weird and intimidating. It says, what is the mass in grams of aluminum that would be needed to produce 4 liters of hydrogen gas at STP? Oh, it says at STP, so what are we going to use? 22.4 liters per mole. All right, we can use that. Go ahead and we'll draw a little map. And we have our grams of aluminum and our 4 liters of hydrogen gas. Let's give myself some room here. All right, so I'm going to start with my 4 liters of hydrogen gas. And now it is just like a stoichiometry problem from a couple of weeks ago. The question you harassed yourself with when you're doing stoichiometry is, well, first, can we use volume ratio? Can I use volume ratio here? No, why? Yeah, aluminum's not a gas. You can't use volume ratio if you're not dealing with a gas. All right, so we can't use volume ratio, so this is just going to have to be stoichiometry. So, can I use mole ratio? No, I have liters. How can I get liters to mole so that I can use mole ratio? Because that's the only way to move around. Oh, yeah, that's coming in handy. All right, liters are here. Liters have to go here. 22.4 liters in 1 mole of hydrogen. Now, can I use mole ratio? So do. Mole of H2 is on top, so mole of H2 here. And then mole of aluminum, where the question mark is. You fill it in with the coefficients. Coefficient for hydrogen is 3. The coefficient for aluminum is 2. Moles of hydrogen are gone. Now I just have moles of aluminum, but they want grams of aluminum. How do I go from moles to grams? Molar mass. So from the periodic table, aluminum is 26.98 grams per mole. Mole is on top, so mole has to go here. And in 1 mole, there are 26.98 grams of aluminum. Remember, when you are doing molar mass, you do not take into account coefficients. Only subscripts. The only time you use coefficients is when you're working on mole ratio. That is it. All right, moles cancel out. All I'm left with are grams of aluminum. Everything on top multiplied together, divided by everything on the bottom, multiplied together. Remember, if you're going to do that in one fatal swoop, it needs to be in one set of parentheses. How many sig figs in my answer? 3. You go by the number given in the problem. I got 3.21 grams of aluminum. All right, does that make sense? All right. So that's with STP. You can use that 22.4 liters per mole as a substitute for using the ideal gas law. In the next type of problem that's not an STP, you cannot use the 22.4 liters per mole, so we will have to use that ideal gas law. Let's go to this next type. Here it is. Okay, this type of problem is not an STP. What is the number one thing you are going to do? Balance. All right, let's see. I've got 3 and 2 for my nitrogen, so I'll put a 3 here, a 2 here, and a 2 here. All right. Now, what volume in liters of N2 gas? So volume's what I'm going to be looking for here in liters. And this volume is going to be measured at a pressure of 1.30 atmospheres and a temperature of 87 degrees C, but we know that has to be in Kelvin. And so what is that? 360 Kelvin. And then the only other piece of information is produced by the reaction of 70 grams of NaN3. All right. As we've started looking at this, we have volume, pressure, temperature. And I told you with these, you are going to have to use the ideal gas law. But really, anytime you see volume, temperature, pressure in a problem, and we're dealing with gases, you should automatically be thinking ideal gas law. So for the ideal gas law, it's PV equals nRT. If I'm looking for volume, let's go ahead and rearrange that. So nRT over P. So we have to have all of those pieces in order to solve for the volume. Well, I have pressure, I have temperature, R is a constant. Which R am I going to use? Is the one that has what in its units? Atmospheres, and that's the 0.0821 liter atmosphere mole K. And so we have that. And the other thing we need is N. What is N? Moles. Okay, now it is going to be, if we do PV equals nRT and solve for volume, we're trying to find the volume of N2. Here's where this is important. It's not just any moles. It is the moles of N2. You cannot solve this problem using the moles of NaN3. It has to be the moles of that same substance you're trying to find the volume of. That's the way the gas law works. So this I need in order to find the volume. And I don't have it. But is there a way, with what we have given, that I can find the moles of N2? Exactly. Use these grams and convert them to moles of N2. Again, just using stoichiometry. Okay, all right. So 70 grams of NaN3. Can I use mole ratio? No. So how do we get grams to moles so that we can use mole ratio? Molar mass. 1 sodium and 3 nitrogens. 65.02 grams and 1 mole. I think that's right. Of NaN3. Now, I will caution you, do not Stop there. It cannot be moles of a different substance. We need the moles of N2. Somehow they got much smaller. All right. So we use mole ratio. Moles of Na, N3 to moles of N2, which is what we need the volume of. Fill it in with the coefficients. 2 and, what is it? N2 is 3. And now I can get the moles of N2. I need 3 sig figs, so what is it? 1.61. That is your N. Once you have that piece, it's just PV equals nRT, just like you did for homework last night. So 1.61 moles times my R, and I'm just copying these down because I already have them written down. Times my temperature, which is 360, divided by my pressure, which is 1.30 atmospheres. Atmospheres cancel, mole cancels, Kelvin cancels, and all I'm left with are liters. How many sig figs in my answer? 3. All right, so 36.6. How you feel about that? All right, again, I know it seemed like it took forever, but it's not. It's an ideal gas all problem. You just have to find the moles of N2 first using stoichiometry. That's it. Do not try and use 22.4 liters per mole on a problem that is not at STP. Okay, because that constant or that little conversion factor is only at STP. This is not too much harder. All right, the next problem is for you guys.